we placed these two input logic gates and we applied inputs and observed outputs. So the input in Proteus environment are basically logic states, and the outputs, digital outputs, can be observed using logic probe. If we want to simulate, we can simply click the run button over here and we can give the inputs and observe outputs. I have used the same inputs and connected them to each of these gates. We can change the inputs and observe the change in the outputs of all of these gates at the same time. The details that we left in the earlier video were related to these pin numbers. You can see where are they coming from and the names of these ICs. So if I zoom in, you can see something like 74LS02, 74LS08, and also the pin numbers. So we need to know the pin numbers and we need to know the functionality of each pin. For example, how do I know that I have to apply inputs at pin 2 and 3 over here in case of 74LS02, and how do I know that I have to apply the inputs at pin 1 and 2 of 74LS08, and the output in this case is at pin 3, whereas in case of 74LS02 it is at pin 1. And more important than that is, how do I know that a 2 input NOR gate is 74LS02 IC. Alright, so all of this information is coming from a document. That document is known as datasheet. So we need to know the number of the IC and then we need to get the datasheet of that IC. So for example, let's say I want to simulate a 2 input OR gate. Alright, so I can go to internet and search 2 input OR gate datasheet, and it would be good if we can just directly get the PDF of the datasheet from the search page. So usually I type PDF at the end. So let's open this one. So, and we can zoom in. So the datasheet basically contains a lot of information, but if we just want to simulate our gates, we don't need to know all of this or go through all of this information. So some of the things that we should note is the word quad, 2 input OR gate, and the number is DM74LS32. DM, the first two alphabets are usually for the manufacturer, they denote the manufacturer. 74 is basically 74, this 74 you see here, this is basically a identifier which shows that the IC belongs to commercial TTL series. LS is low power Schottky diode, which is a technology, a diode technology that is used in manufacturing of these ICs. Alright, we don't need to go into details of low power Schottky, the characteristics of that. And the 32 is basically the identifier for 2 input OR gates. And if we read this description, it says quad 2 input OR gate. Quad here means that this IC basically contains 4 2 input OR gates. And in the general description, you can also read that this device contains 4 independent gates, each of which performs a logic OR function. Alright, so how does the IC physically look like? Remember when we were placing these ICs in Proteus? So let's say I want to place an IC 74LS00. So in this PCB preview window, you can see that how the IC physically looks like. And another thing, DIL14, it is dual inline, and 14 is the total number of pins in this IC. Alright, so the similar diagram, a similar looking diagram, you can find in the data sheet as well. Alright, so this is the connection diagram, and this is the function table. So in function table, you can easily identify that this is the truth table for an OR gate. The truth table is sometimes labeled as function table in the IC. So it's the same thing. And this is the connection diagram. A few very important things to note here. 7 pin is for ground and 14 pin is for VCC. So VCC is usually the operating voltages of ICs, and for TTL family, this is standard at 5 volts. It can go to 5.5 or 4.7, 4.8. So this information is also available in the data sheet. In Proteus, when we are trying to simulate an OR gate, what we are doing is basically we are going to we are in fact placing this IC74LS32, and in this IC there are 4 gates, and we are going to place one of these OR gates over here. So you can see it over here that you have U4A and 74LS32. So if I just place another OR gate, so let me select another OR gate and I just click it. All right, another thing, you have to first stop and then click to place an element. So if I let me just bring this down. So this is U4, this is the IC identifier in this schematic. This is U4A, U4B. Now you can relate these two to the data sheet. So the pin 1, 2, so there are 4 OR gates. The pin 1 and 2 are the inputs of the first OR gate, you can say, and the output is at 3. And then we have inputs at 4 and 5, and the output is at 6. This environment is placing these gates, these individual gates, but they are still part of the IC. So you can see the pin numbers, and this U4 identifier basically tells you that these two gates belong to the same IC. Alright, we can now delete this one because we don't want it. So let's go through the data sheet and see what other relevant information we can find. Alright, again you can see something like dual inline package DIP. Alright, so we have a dedicated video as well which related to this information of packaging of ICs. Dual inline means that you have pins on both sides of ICs. Since we know the IC number, so let me just type 74LS32 and see what comes. See, so that's how a physically IC looks like. Alright, but in Proteus environment, instead of seeing this IC, you are seeing these individual gates. We have the supply voltage, which is minimum 4.75, the nominal is 5 volts and the maximum is 5.25, and we also have absolute maximum ratings. Alright, so it can go up to 7 volts, and you see a note and it says that the absolute ratings are those values beyond which the safety of device cannot be granted. The device should not be operated at these limits. 5 volts is good. And similarly, just like operating voltages, we also have the values for the logic low and logic high. So if you give a signal of 2 volts or above, this IC is going to consider it as a logic level high, and if you give something like zero point 0.8 volt and below, it is going to consider it as logic level low. And similarly, you can have the output current and the input current things, and these are more electrical characteristics. Switching characteristics tell you something like if the logic level goes from low to high, so how much time is it going to take? All right, but again, these are more tiny details which we are not trying to grasp right now. And you can see physical dimensions of the ICs as well for different packages. So this is the physical dimension for the DIP package, dual inline package. The IC is also available in other packages as well. So the only information we are concerned is the operating voltage and the voltages for high level input, logic high input, and logic low inputs. And of course, the function table is important and the connection diagram is important. Another thing you notice is that when we are, you know, trying to simulate these gates, and in Proteus environment, we are placing these gates, so we don't see these pins, ground and 14. So these ground pin and the 14 pin, which is the supply voltage or operating voltage, they are hidden. So whenever we place a gate, we don't find the pin 7 and 14. Alright, so we only see the pin 1, 2, 3. So I have downloaded the datasheet for all of these gates. Let's go through them and see what informations can we find. So let's open this DM74LS86. Again, you can see the description. The device contains 4 independent gates, each of which performs a logic exclusive OR functions, and this is available in a lot of packages. This is the connection diagram. This is the function table. You have the inputs at pin 1 and 2 and the output at pin 3. And this is the function table. You can see the Boolean equation for the exclusive OR function as well. Supply voltages, electrical characteristics, some physical drawings. Let's open the data sheet of 74LS00. It says quadruple 2 input positive NAND gates, and it is from the manufacturer Texas Instrument or TI. It's a very well known company, and you can see the features. So it says package options. These are different package options, applications, logic diagram, and this one is a very detailed datasheet. It has 35 pages. So some of the information would be relevant to us, some of it would not be. So the pattern is very much similar. We have supply voltage, we have high level input voltage, low level input voltage, thermal information, some internal diagrams, and over here we have the function table as well. You often find an X written for inputs or any other signal, so it basically means that B is don't care, or you can say it's a short way to write our function table. Instead of writing low, low, and then low and high, we can just write low and X as long as our output is the same. And similarly, you can see if the input A is low or high, as long as the input B is low, the output is same or high. So this is just a way of abridging our function table, writing it briefly. This also shows a typical application going through the datasheet layout and some a lot of information. We are not interested in it. Oh, and it even has a diagram for the dual inline or dip package of the 74LS00. SN over here means the manufacturer, and 54 is for military grade TTL IC. 74 is for commercial grade, 54 is for the military grade. So if we go to the top, we can see the same data sheet contains the information for the military grade and the commercial grade. So many a times you can see the file name of the data sheet is named maybe using 54 or 74, but inside the datasheet it contains the information for both the commercial and the military grade ICs. Let's go through the other data sheets, maybe 74. All right, so you can see this one is quite old, so many a times that these are basic gates and the data sheets don't change. So on internet you may find across scanned versions which look like very old written documents. Again, in the function table you can see that you have x returns, and this row basically means that the output is same for input A being high and input A being low. You can see the description. The device contains 4 independent 2 input NOR gates. Here the input pins are pin 2 and 3 and the output pin is 1. If we see this IC of exclusive OR, the input pins are 1, 2 and the output pin is 3. So it is not always the case that the input pins are going to be numbered 1 and 2 and the output is 3. For 2 input gates, it might be that the input pins are 3 and 2 and the output pin is 1. So we can also see this in the Proteus over here. You can see that NAND gate, AND gate, OR gate, exclusive OR, all these four have inputs at pin 1, 2 and the output at 3. But this NOR gate, it has inputs at pin 2 and 3 and output at pin 1. Let's open the last data sheet we have. I think we missed one. Which one? 08. Yes, so we have all the data sheets open now, and we can see their function tables, their logic symbols, logic diagrams, the function they are implementing. So mostly we are interested in this information as long as we want to simulate. Again, you can see 08 is for AND gate, 32 is for OR gate, 02 is NOR, 00 is NAND, 86 is exclusive OR. So to summarize, in this video we have looked at the data sheets for the ICs we used in the first video. We looked at things like 74LS00, 74LS02, where are these numbers coming from, how do we get to know where we have to place our inputs and outputs. In case of basic gates, it is quite easy to know where to place your inputs and observe outputs, but in some complex ICs it is not that obvious. Hopefully with this video now you are in a more comfortable position to find the data sheet of a IC, read the relevant portions of a data sheet, and you also know where to provide the inputs and observe outputs, and where are these numbers 00, 02, 08, 32, 86 coming from. Don't worry if you can't remember these numbers. As you get used to these ICs, these numbers would not be a problem for you. In the next video, we are going to talk about the logic families. So see you in the next video.